Assalamualaikum and hello everyone. My name is Rahman Izal bin Rahmat and my matrix number is CE250103, and today I'll be talking about the introduction for our project. So what is the main goal for our project? Which is to maintain voltage stability and grid efficiency, and it is a critical requirement in industrial power system. Industrial plants rely heavily on AC networks to drive heavy inductive equipment like induction motor, which demands both active power, which is P for mechanical work, and reactive power, Q, to sustain internal magnetic field. So for this project, we investigate a steady-state single-phase AC parallel T network, modeling a plant fed by two separate supplies, which is a primary grid V1 240, and the magnitude is 0 VRMS, and a backup inverter, which is 220, and the magnitude is 30 dB VRMS. Power is delivered through distribution feeders with distinct line impedance Z1 equals to 4 plus J3 ohm, and Z2 equals to 2 plus J2 ohm. Operating under option A, which is small motor load, that our group choose, the plant features an updated load impedance of Z load, which is 12 plus J16 ohm. This is the value that our group decide on after discussing. And to evaluate the system, our group utilized a comprehensive suite of linear circuit analysis technique, specifically source transformation, nodal analysis, superposition, Thevenin theorems, Norton theorem, and mesh analysis. This is all the calculation method that will be separated by members to solve for the network parameters. We then validate our theoretical finding inside the fast start simulation to analyze the gate voltage drop, power factor, and waveform phase relationship. Next, I'll be talking about the objective that we need to achieve in this project. So, what are the main objectives that we need to project following the instruction task? The first one is to manually solve the dual source network using all the six calculation method that I've mentioned earlier. The calculation method will be separated by each member, and we need to find the mathematical results. And the second one is we need to determine the steady state load voltage, which is V load, total line current, I load, and operating power factor, PF, at the industrial hub. And the third one is we need to calculate the active real power, P, reactive power, Q, and apparent power, S, drawn by the complex load. The fourth one is we need to derive the equation for instantaneous voltage V load T and current I load T at 50 Hz, which is our frequency value, to map the inductive phase lag. And the last one is we need to model the gate in the fast start environment, which is we need to use the fast start to stimulate our circuit to prove that our mathematical solution is the same as the simulation value.
Now, let's look at the foundation parameter of our system, which we have carefully configured to model realistic industrial scenario. The system operates at the standard utility frequency at 50 Hz. As you can see in the table, our network powered by two distinct AC voltage source. Source 1 provides 240 volt at the reference angle of 0 degree, while source 2 operate at 220 volt with a phase shift of 13 degree. The source delivers power through two separate transmission lines. Line 1 has an impedance of 4 plus J3 ohms, and line 2 is represented by 2 plus J2 ohms. Finally, our load categorized as medium industrial load, possessing a impedance of 12 plus 16 J ohms. This inducting component represents typical factory of machinery loads. This precise mathematical setup serves as the groundwork for all our subsequent simulation and analysis. For the next slide is false start simulation model. To analyze and validate how these parameters interact under the real-time condition, we model the entire AC power delivery system using the false start circuit simulation. In this simulation model, the two AC sources are connected directly to the load through their respective transmission line impedance, just as we define in our parameter. The load is clearly constructed using 12 ohm resistor in series with inductive resistance of 16 ohm. To observe the steady-state electric behavior, we integrate V12 measurement tool into the circuit, specifically a voltmeter and ammeter and a wattmeter. Under simulation, the wattmeter record an active power delivery of 1.26 kW directly at the load. Furthermore, the real-time wave oscillation display at the bottom of the screen allow us to visually monitor the phase shift and steady-state stability of our AC waveform.
Okay, we move to observation. So, first, sinusoidal stability. Both voltage and current maintain stable pure sinusoidal shape at 50 Hz, confirming normal AC operation. Phase shift, a distinct time gap is observed where the current waveform, yellows, lags behind the voltage waveform, green. So we go to inductive nature. This lagging behavior serve as empirical proof of the highly inductive load in the facility. Continuous power sink the power waveform wide oscillate entirely above the zero axis, showing the constant average power observation of 1.267 kilowatt.
Next, we move to electrical parameter measurement slide. Uh, in this slide, we can see the exact value extracted from our simulation. Compile this data matrix. From the simulation, our low RMS voltage is 205.035 volt and the RMS current is 10.265 ampere. The measured real power from the wattmeter is 1.267 kilowatt. Based on this reading, we calculate the apparent power to be 2.105 kilovolt ampere and the reactive power at 1.681 kilovolt ampere reactive. This leaves our system with a power factor of 0.602 lagging with a phase angle of 53.02 degrees. To conclude to our analysis, a low power factor of a 0.602 is inefficient because it causes a high reactive power circulation of a 1.681 kilovolt ampere reactive in a system. Therefore, this highlights a critical need for us to implement power factor correction or PFC capacitor bank to optimize the system overall efficiency. That's all.
My name is Muhammad Fahmi bin Muhammad Mansur. My matrix number is CA250099, and this is our group validation and comparative analysis. Firstly, our theoretical value that we get for our VLOAD is 205.6 volt, and our simulation value is almost the same, which is 205.564 volt. Our percentage error is 0.018%. And next, our current load, which is our theoretical value is 10.28 ampere, and our simulation value is 10.278 ampere. Our percentage error is 0.019%. And our power factor that we got for our calculation is 0.6, and our simulation value are almost the same, which is 0.595. Our percentage error is 0.83%. Our real power that we calculate is 1268.5 watt, and our simulation value is 1260 watt. Our percentage error is 0.67%. Our reactive power theoretical value is 1691.4 VAR, and our simulation value is 1698 VAR. And our percentage error is 0.39%. Our apparent power is theoretical value 2113.6 VA, and our simulation value, which is 2112.8 VAR or VA. Our percentage error is 0.04%.
Hi, my name is Kuhan. My metric number is DE230141, and today I'll be presenting about the engineering discussion. So, for a voltage current phase relationship, the simulation results clearly demonstrate the phase relationship between voltage and current in an inductive AC power system. Due to the inductive characteristic of the medium industrial load, the current waveform lags behind the voltage waveform. This occurs because the inductor stores energy in its magnetic field and opposes sudden changes in current. The measured phase angle is approximately 53.575 degrees, confirms the presence of significant inductive behavior within the load. As a result, the system operates at a lagging power factor of 0.595, indicating that not all supplied power is converted into useful work. The simulation successfully verifies the theoretical concepts of AC circuit analysis and highlights the importance of power factor considerations in industrial electrical system. Thank you. So, in conclusion, the single-phase AC power delivery system was successful modeled and simulated using Falstad circuit simulator. The simulation results showed excellent agreement with the theoretical calculations obtained in part 1 of this project, with all percentage errors remaining below 1%. The measured values of load voltage, load current, power factor, real power, and apparent power, reactive power closely match the calculated values, confirming the accuracy of the analytical method used. Furthermore, the simulation demonstrated the effects of inductive loading, including current lagging voltage and reduced power factor. Overall, the project successfully validated the theoretical analysis and demonstrated the practical application of AC circuit principles in evaluating industrial power delivery system performance. Thank you.